Formal charge is a bookkeeping measure that we use when drawing Lewis structures to evaluate if we've drawn the best Lewis structure for a molecule. A formal charge is a hypothetical charge. It's the charge that each atom in a molecule would have if its electrons were shared equally and truly equally. We can determine formal charge by counting up all the dots and dashes around an atom and subtracting that count from the number of valence electrons that that atom has as a neutral substance. More rigorously speaking, the formal charge is the number of valence electrons minus the combination of unbound electrons and half of those bound or shared electrons that an atom uses in a covalent bond. When we calculate the formal charge, we're going to want to look for three specific things about our molecule's formal charges. For one thing, all of the atoms should get as little formal charge or as close to zero formal charge as possible. If possible, we would like to have every atom feel zero formal charge. That would mean that it hadn't gained or lost any electrons and it was truly sharing them. It's sometimes unavoidable to have a non-zero formal charge, particularly when we're dealing with polyatomic ions. We have to have at least one atom that doesn't have a zero formal charge in the Lewis structure somewhere. When this is the case, if more than one atom has a non-zero formal charge, then we'll want to arrange our Lewis structure in such a way that adjacent atoms never get the same non-zero formal charge. And by the same token, if atoms must have a non-zero formal charge, then arrange your Lewis structure in such a way that the most electronegative atom in the molecule gets the most negative formal charge. This would mean that that atom is drawing electrons toward itself more efficiently, and that's exactly what we expect from a highly electronegative substance. Ultimately, all the formal charges that we assign to atoms will add together to give us the overall charge of a molecule or ion, 0 if we're dealing with a neutral molecule, and the charge of the ion when we're dealing with a polyatomic substance. Formal charges are not the same things as oxidation numbers. They're just a bookkeeping method to help us evaluate on a case-by-case basis the validity of a Lewis structure. So let's talk about how we use these things. Here I've drawn the Lewis structure for the molecule formaldehyde, whose formula is CH2O. There's a central carbon atom with a double bond to an oxygen and single bonds to two different hydrogen atoms. We're going to calculate the formal charge on each atom, carbon, oxygen, and both hydrogens in this molecule. We can start with any. Maybe I'll start with the oxygen up at the top. To calculate formal charge, I'll take the number of valence electrons that oxygen has, which is 6, and subtract from that the number of dots and dashes that I see in this Lewis structure. There are a total of 1, 2, 3, 4 dots, and another 1, 2 dashes. So that's a total of 6 dots and dashes. 6 minus 6 is 0. We say the formal charge on that oxygen atom is 0. For the central carbon atom, the formal charge is equal to the number of valence electrons that carbon has. Carbon's in group 4A. It has 4 valence electrons. In this Lewis structure, there are no dots or lone pairs of electrons around the central carbon atom, but there are 4 bonds, 1, 2, 3, 4 dashes. So to calculate carbon's formal charge, I'll say that it's 4 minus 4, or 0. For both hydrogens, we can calculate a formal charge by subtracting from the total number of hydrogen valence electrons, that's 1, the total number of dots and dashes around each hydrogen. Each hydrogen only has 1 dash around it, so the formal charge on each hydrogen is 0. This is a good Lewis structure for formaldehyde because every formal charge on every atom in this molecule is 0. So with formal charge explained, let's talk about how we use it to evaluate a Lewis structure. Let's draw a Lewis structure for phosphoryl chloride, POCl3. To draw our Lewis structure, we'll need to have an electron budget, 5 valence electrons for phosphorus, 6 for oxygen, and 7 for each chlorine, and there are 3 chlorines. In total, our Lewis structure for POCl3 should contain 32 electrons. The least electronegative atom in this bunch is phosphorus. We can draw its Lewis symbol right at the center of our molecule, and I'll place oxygen and 3 chlorines all around it. Then we can connect those dots, making a bond between phosphorus and each of the 3 chlorines, and a bond between phosphorus and oxygen up at the top. You'll notice, though, that our phosphorus feels 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons around it, while oxygen only feels 1, 2, 3, 4, 5, 6, 7 electrons around it. One of the ways that we can approach this issue is to get rid of an electron on phosphorus and transfer that instead on up to oxygen. This makes both phosphorus and oxygen feel 8 electrons and a complete octet around themselves respectively, but it begs the question, why didn't we share an extra electron between that oxygen and phosphorus to make a double bond? Why don't we evaluate what would happen if we did? If we did share that extra electron as a double bond, rather than shuttling an electron from phosphorus over to oxygen, our phosphorus would feel 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons around it. It is possible for phosphorus to expand its octet because it is in the 3rd period of the periodic table and so has d orbitals accessible to it. For more information about expanding octets, refer back to the video on exceptions to the octet rule. But now we have 2 Lewis structures that could represent POCl3. Which one is better, and is there one that is definitively a best Lewis structure? In order to answer this, we're going to need to determine formal charge. To determine formal charge, again, we'll think about the number of valence electrons that each atom has, and subtract from that the number of dots and dashes we drew around that atom in our Lewis structure. For the oxygen in the top Lewis structure, for instance, our formal charge is oxygen's number of valence electrons, 6, because oxygen's in group 6A, minus 1, 2, 3, 4, 5, 6, 7. In total, the formal charge on oxygen is -1. For each of the chlorines, the formal charge is equal to the number of valence electrons that chlorine has, 7, minus 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. The formal charge on each chlorine must be equal to 0. And lastly, the formal charge on our central phosphorus in this top structure is 5, as phosphorus has 5 valence electrons, minus 1, 2, 3, 4. 1 for each dash around it. 5 minus 4 is +1. If we apply that same thinking to the structure that we drew down below with a double bond in it, the formal charge on the oxygen is equal to 6 minus 1, 2, 3, 4, 5, 6. That's 0. The formal charge on each chlorine hasn't changed. That's 0 in every case, just like above. But the formal charge on phosphorus is now 5 minus 1, 2, 3, 4, 5. The formal charge on our phosphorus is now 0. In the structure that we draw at the bottom, with a double bond between phosphorus and oxygen, every atom gets 0 formal charge. Our goal when drawing Lewis structures should be to minimize formal charge and give every atom 0 formal charge whenever possible. With that in mind, the best Lewis structure for phosphoryl chloride is the one on the bottom that has a double bond between our central atom and oxygen up above. This is the true Lewis structure for POCl3, and it's the best Lewis structure because formal charges have been minimized.